Start time. So let me go ahead and begin and get us started. I will start first by mentioning there's a few more labs going around for you to pick up. Many of you have probably noticed that the grade sheet finally there online, if you got a chance to look, is finally filling in and has a lot on there. So I'd encourage you to look at that. In particular, you're going to want to see that as we get towards the end. I guess we are near the end, but that's where I will put your scores from test number 3 and the final exam. And so just to kind of summarize what we have left, which is very little here, is this is our last week of lecture, and then that's followed by final exam. So believe it or not, 1 week from today, you will be halfway through with the final exam. And so we have really just 1 week and 1 hour left. And so here's what we have left. We have today's lecture, and so today's lecture is going to lead into 34, what little we can do on 34, and that's when I want to show you. There's one last tidbit of physics that you must see, and then I'll kind of summarize everything, and we'll call it quits, and it's best we could do this semester, and it's kind of the end of this level, but it'll definitely set the stage for your next level, which many of you will go on here on the next level. So lecture today. Next Thursday is the exam, your last in-class exam. That is then followed by your final exam next Tuesday, and I should emphasize Tuesday, what time? 8 a.m. All right, so make sure you are here at 8 a.m. because they'll be kicking us out of here a little bit after 10 to get ready for the next class that comes in. Looks like our door's locked here. Hey, come on in. Oh, there's a whole group of you out there. All right, good. Yeah, our wonderful new automatic doors. Never had so much troubles with doors and doors locked till they get these automatic ones that are supposed to save us the hassle of unlocking and locking them. And nothing has been more of a hassle than these automatic locks. All right. So those of you coming in, I hope you caught that. It's worth repeating. When is your final exam? I don't know. Tuesday. What time? 8 o'clock here. All right. And so what we're about to do here is put some closing remarks here to this last part of the chapter. Don has a review set up for you, so before I pull down the screen, wanted to point that out. So today, 2:30 to 5:30 will be your review, and so your test will include up to wherever we get today. And so we're going to do a little bit of 34 and hopefully what I would call the most significant stuff of 34. The stuff that you'll see here is not nearly as mathematically intense, but conceptually real important. Like I said, one last bit of physics, and then we'll kind of summarize the semester. Did that go on? I guess I didn't turn it on. All right. And so let me begin today with some final remark of really chapter 33. I don't know if you caught it as you were reading along there, but there are the last two sections of chapter 33 that we didn't quite get to. And I want to point those out. If you'll remember from the last time we met, we finished up the grand finale with those LRC circuits. And doing that LRC circuit, we learned a little bit about phasors and RMS, but the big idea was what happens if you have an inductor, a capacitor, and a resistor all together in the circuit. Now let me not repeat that, but let me point out then the last two sections of 33 is section 8 and section 9. Just because we're out of time, we're going to skip section 9 altogether, although you kind of saw me run a little experiment with filtering and the different frequencies. So you kind of saw it, but don't worry about the homework, won't be on the test. But the transformers on section 8 are extremely important. So I thought I would begin there. And so let's take our first 20 minutes or so and say, what are transformers? And here's the idea. And so I thought I'd begin by kind of showing you, what if you did the following? What if you took an AC source, as we've been talking about in this chapter, and ran it through a solenoid, a coil? That's the first half of our transformer. So I'm going to take the AC source and I'm going to run it through a coil. Now, of course, that's going to produce some flux and some changing flux because the current is changing. In fact, let me write it this way. I would write this at, okay, let's call this the EMF on the primary side. And so I'll put a little p there for primary. That would be equal to, and I'll put the negative sign there, although oftentimes we skip the negative sign. That would equal to the number of turns in the primary times the change in flux. And so there is an EMF established in that, if you want to call it, an inductor. Okay? I'll start off doing mine by saying, well, here's what I'll take. I will take this coil. Unfortunately, since it is wrapped with black electrical tape, you can't see the many wires. Maybe you can begin to see them right here. But it says on the top side that there is 110 little turns of wire. And so what I'm going to do is take, an AC source. So here is my AC source. I'll scoot this down a little bit here. But I have this plugged into the wall, and in fact this is actually a transformer in itself. I'm going to show you the operation of this. This is reducing the voltage so that when I have some voltage here, I have about 7 volts, and so that I don't have to worry about the higher 120 volts here. And so that's the point of this transformer. So I just wanted to get some AC voltage. And so there it is, and I'm going to put it into this coil. Not quite yet though, because then there's going to be a second coil. In that picture, they show a little magnetic bar that is in the shape of a rectangle or a square, and then they show a second coil. Let me call this number of turns in the secondary. And for me, I will grab this one over here. Here is a coil with, I'll grab this one, why not? This one, and again, unfortunately, you can't quite see the wires, but it says that there are 55 turns here. So that will become my secondary in just a second. But here's my question. What then is the EMF produced in the secondary? Now you can see this goes all the way back to Faraday's law. Because Faraday's law says, well, why would there even be a voltage here anyways? Well, remember, there's a voltage produced if there is a change in flux. And so essentially here's what we have happening. On this side, on the primary side, we have a changing current. The changing current makes a changing flux. That flux then is fed into the secondary. The changing flux in the secondary then produces a voltage in the secondary. But here's why they're called transformers. Is the voltage in the secondary necessarily the same voltage that we started off in the primary? No. Let's run through the math here. On the secondary side, I would have minus the number of turns in the secondary times the change in flux. Now you may argue that that would be the change in flux in the secondary. And so the amount of flux that is produced in the primary, in a perfect world, would all go into the secondary. Now, you see, when I hook this one up, we won't get 100% of the flux that is generated in the primary to go into the secondary, but we will get something reasonably close to that. But here's the math I want you to see, and the whole reason for the name transformer. If I take the voltage of the primary and divide it by the number of turns in the primary, doesn't that give me the change in flux here in the primary? And if I do the same thing with Faraday's law in the secondary, both of these would be equal to negative the change in flux. And in an ideal world, if I could get all the flux from the primary, so this one, to go into the secondary, this one, then these two numbers are equal. And so, like I said, in a perfect world, let's say they are equal, but here's what happens. The voltage in the primary then, divided by the number of turns in the primary, is equal to the voltage, or the EMF, in the secondary, divided by the number of turns in the secondary. If I then rearrange this equation for the voltage in the secondary, notice then I have an equation that says the voltage in the secondary isn't necessarily the same as the voltage in the primary. It can be either stepped up or stepped down, is the word we like to say. Depends on the number of turns. I should say the ratio of the number of turns in the secondary to the primary. And so if I start off and build something like this, and I say, all right, let's take, and here's my magnetic material here. I'm going to take this apart and say, let's take this first coil. Let me put it right on my soft iron piece and feed this into my primary. Now, so I have something to look at. I will hook up the voltmeter here and say, all right, I have roughly 7 volts. And so what is coming in to my primary right here is roughly 7. Now, remember, the number of turns in the primary, I said earlier, was 110. Let me take another coil. This one is 55, purposely half of the 110. So if my secondary coil has half as many, 55, compared to 110, then what do you expect here for the voltage in the secondary? Yeah, half. And so this is our primary. Let me direct press it down here a little bit. But if I can get all the flux to travel through the iron pieces and go from the primary into the secondary, this 7 volts should now be reduced down to half as much. And you can see it's a little bit under half, which tells me I probably have not met this condition where all the flux from the primary goes into the secondary. A few of it is not going in there. And so this is what we refer to as a step-down transformer. I have transformed the voltage, in this case, in a downward direction. And that's kind of what my picture illustrates, that I have more turns in my primary than my secondary. It's also what is exactly going on in this, because I had plugged it in to 120 volts, ran it through a step-down transformer so that it would be a 7 volts and be something that would be safe for me to work with, and something that is still oscillating at 60 times a second. Yeah.
The humming sound that's making here, is that similar to the ones that like you see on power lines?
Okay, well, exactly. Now you must remember, and particularly you hear it here, and then I got too many wires in the way to hook this back together. But the idea of hooking it back together and clamping it is to stop those vibrations. Because remember, then, when we were introduced to Faraday's law, The flux that is going through here then makes eddy currents in here. And when the eddy currents are made in here, then they become an electromagnet, and they oscillate like you saw that ring when I did Faraday's law. Anyways, and that's the vibration. So the vibrations are a sign that I'm getting the eddy currents and I'm losing some of my energy. And so it's not something I want, but something unfortunately I deal with. In fact, if you look closely, this magnetic bar is deliberately made not of one solid piece of metal. Otherwise, I'd get a lot of eddy currents. It is deliberately made with bands of iron material to keep the currents from being unable to go around in a circle. And so that helps me with my little transformer. I'll pass these around while I'm talking, but these are the ones that we dealt with in lab, kind of. Do you remember with the lab we did where we changed, it was the oscilloscope one, it was the part 3, where we changed an AC into a DC? And we, of course, the main point of that lab was to get you to understand how to operate the oscilloscope. But the transformer is these little plugs that I'm sure you see all the time when you, like, say, have your cell phone or your iPad, and you go, what you do is you plug this into the wall. And so this one we've taken apart so you can actually see this is what would plug into the wall, 120 volts. There's the number of turns in the primary. There's the number of turns in the secondary. There's a lot less turns here in this secondary, and the voltage is going to go way, way down. And so we change all of a sudden 120 volts into something much, much lower, and usually around 5 volts or something. Now, that's still AC though. And so if you remember from the lab, but not really covered here in the lecture, you can flip this up and you can see the 4 diodes and the capacitor that is hooked to there, that we did the 4 diodes for the rectifying and the capacitor to build up the charge. This one here doesn't have that. It just steps the voltage down, and so we still have a low voltage, but we still have an AC, so there's no bridge rectifier on it. But while I'm talking, I'll send those around. Did you have a question?
So is anything sacrificed or gained when you step up or down?
I'm glad you asked. But let me show you a few more before I go to the advantages and disadvantages and why we'd even want to do all this. But I'll start with this. Let me first kind of disconnect my primary and take my secondary. And this is what I called a step-down transformer. Let me replace it. This has 220 turns. So that is twice as many as the primary. And again, the idea being here, this would be a step-up transformer. This then would have a ratio of 2 to 1. So if this is 7 volts times 2 to 1, I should be getting about 14 volts out of this. And so this should increase my voltage to about 14 volts. And so, again, looks like I have about 7 going into the primary, and I'm short of 14, of course, because I don't get 100% of the flux from the primary into the secondary. But I think you get the idea. I've roughly doubled the voltage. And for one more shot at it, why don't I take off this one, which is 120, and go to the largest one I can come up with. This is 880 turns. So this is 8 times the number of turns. So there's 7. 7 times 8 is, what, 56? It's not going to be perfect. So hopefully I'll get somewhere in the neighborhood of 50 volts. And a little more voltage than I want to touch or mess with. So let me just make sure everything's clear and begin. And it looks like I get 52 volts. And I get the little lightning strike there saying, okay, danger, you've exceeded 30 and you might shock yourself. So I don't know if you noticed that when we did the high voltages ones. I think the only time we did the high voltages, we had those 70 volt ones and 100 volt ones where we did the acceleration of the electrons, and we didn't, we never used this. So that was the one that we were in that neighborhood of careful, dangerous, and the little lightning bolt shows up there. All right, so there's the idea of the transformers. Now, to your question. Your question is, well, what do we gain? Why do we care about this? Oh, actually, here's a fun one to pass around. Here's a real one that is right out of that same microwave that you saw the magnetron from. Now, why not? I'll toss this around too if you want to see it. But you can feel how heavy it is because of all the iron material that is inside of it. All right, now, do we gain or do we lose anything? Well, keep in mind that this is only half the story, at least when we're dealing with energy. Because if we are talking about the power that is being fed into the primary, I'll call it P primary, that would be the current in the primary times the voltage. And I don't know, should I use a V or an EMF? For some reason, I started to use an E for the voltage instead of the V. And so maybe I'll stick to the script E. But what I guess I'm saying here is right now, I have this set up to be a step-up transformer. It's an 8-to-1 ratio. And so I do know that the current in the primary times the voltage in the primary, that is the energy that is being fed into the primary. That energy gets hopefully transmitted, and in a perfect world, 100% to the secondary. And that's not going to happen, but I mean, I can even fill this one, and it's warm. So I know it's not perfect, but it's reasonable. And so then I would have current in the secondary times the voltage in the secondary. And here's what I'm trying to say. What I'm trying to say here is I could step up or down the voltage, and the corresponding currents would step up and down exactly the opposite. So when you ask this question, is there anything to be gained or lost? I would say, well, there's advantages and disadvantages. One clear disadvantage is we are not getting 100% of the flux. We are getting a little bit of eddy currents. So we are getting a little bit of warming effects. So we're not getting 100% of the energy transmitted. So I would say that's a negative thing. And so all these little transformers that are plugged in, many of you probably still have the charger on your cell phones plugged into the wall right now. Well, it's making eddy currents. It's probably a little warm to the touch. It's consuming electricity. So probably best if you just unplug the crazy thing there, because as it sits there, your TV, your DVR, they're all slightly on. Part of them is just a memory going, okay, hit the remote, hit the remote, hit the remote, hit the remote, and waiting for you to hit the remote for power to go on. And so it's consuming electricity for that, but it's also consuming electricity, what we often refer to as vampire energy, just because it's plugged in. And so the best thing to do is just unplug it. I know here where we work, we're coming into the semester. I'm sure I will get an email about the week after finals week, and they'll say, hey, semester's over, students are gone, I'm sure you're getting close to finishing up your grades, but as soon as you are done with your grades, before you leave campus for the winter break, could you go into your lab and unplug, because you know those 15 computers we have in there, can we unplug those? We got to have a lot of equipment in Don's area, and unplug those. Unplug the power strip on my computer, because again, why for 4 weeks should all those computers sit there and just suck up electricity? And so we usually just turn them off for a long time, and when we're gone a long time. Don usually does it overnight. I don't know if you noticed, but at the end of the day, he'll always go and shut the computers off, and then he'll do the power strip, and he shuts the power strip. You may have noticed that the opposite. When you come in to turn on the computers, you go, hey, it won't go on. Oh, the power strip's off. Who keeps turning that power strip off? But that's why he keeps turning off the power strip, to kind of stop that vampire energy. Yeah.
Do things like the lights that are like connected directly into the circuits of the building, do those also consume electricity?
Not if they're, no, because they don't usually go through a transformer. Okay, and so again, the transformer, again, because of that vibration, those eddy currents, just because it's sitting there, it will be consuming some electricity there. And you can see why. I mean, there's a direct path. And so if this is not hooked up to anything, in an ideal world, you would say, okay, my secondary, nothing is hooked up, no current. So then I get no current in my primary. In a perfect world, but the reality is you're going to get a little bit of current in there. Well, what I was getting at in all of this is that this same ratio, the ratio of the secondary to the primary, the voltage, is exactly the same as the ratio of the primary current to the secondary current. And so if I leave the currents alone and say, let's take this ratio, then I will get number in the secondary to number in the primary. If I solve this equation for usually what I'm interested in, which is what is the current in the secondary, then I would have number in the primary over number in the secondary times the current in the primary. So again, you can see that as the voltage, let's say, is stepped up by a factor of 8, since that's what I have here, if I step this voltage up by a factor of 8, then what do you say about the current? The current goes down by a factor of 8, such that then the power coming into the primary is equal to the power coming out of the primary. So the advantages and disadvantages are, of course, I lose a little bit of electrical power because of this added little metal piece here, this transformer, but that could have some advantages, and that's kind of the last piece of the puzzle I want you to show you. Some of you, and we've been kind of touching around the edges of this for the last couple of weeks, but some of you have pointed out that our electrical grid is an AC grid. Why? And it's really this physics right here of why the electrical grid ended up being an AC back in 1890s, 1895. And here was the idea. What if I were to do something like this? What if I had a bunch of homes starting in New York City, and I want to change the lights from kerosene to electric? Well, I got to generate that electricity. How do I generate that electricity? Well, I can build a generator. And the first ones were pretty straightforward. They were moving magnets. They had a little engine. The engine would run, and as the engine would run, it would have a magnet stuck to it, and the magnet would spin. But where are you going to put this little generator? Well, if you're wealthy enough to afford electric lights, you're probably also wealthy enough to have a basement and a lot of room. And so these rich mansions on Fifth Avenue, New York, they would have their own generators. And so down here somewhere, we would produce our electricity. And it wasn't a real big deal. You would just send the electricity kind of, oh, well, it's already in the house, whatever the house looks like. And, and all you got to do is send it to the wiring in the house here. But let's expand this. Let's say we don't want to have a generator at every house. What if we would like to make one giant generator that could power a whole city, which is how we do it today here. Watch this. What if I were to take a wire, and just for the sake of discussion, let's take a wire that has a diameter of about 1 inch. Then, so if you've seen these big power lines here, they're pretty good size. I mean, they can have a diameter of 1 inch, and they string across, okay? And they're usually made out of steel, though, so that they're strong. But let's just say we have 1 mile. 1 mile is not very far. We're probably getting some of our electricity from hundreds of miles away. It wouldn't surprise me if some of our electricity right now is coming from Hoover Dam and some of the other power plants. And we've got 2 big ones on the Oxnard Plain, and that's a good 20 miles of wire right there. But let's just talk about 1 mile, okay? How much resistance would you have in this steel cable that is 1 inch in diameter and 1 mile long? Well, this will take us all the way back to chapter 27, I think, but the resistance would be rho times L over A. And so I'll flip over here to chapter 27 real quick and say, what is the resistivity of iron, steel? Well, it looks like it's about 10 times 10 to the minus 8. So I'll put 10 times 10 to the minus 8. How long is this wire? Well, I picked a mile. That wasn't very good scientific numbers there. Let me change it to meters here. So 1,609 meters. I'll take that in terms of its length. Its area, its cross-sectional area. Well, I guess that would be pi times its radius squared. Again, I picked 1 inch, so that wasn't real good science numbers there. But we know about an inch is what, 2.54 centimeters. Let's just call it 2.5. Cut that in half, and that would be 125 centimeters. And so I'll convert it to meters, and I'll square that. And so this would be the resistance of 1 mile of wire. Now, not much resistance, I don't think here. Let's see, 10 times 10 to the minus 8 times 1,609 divided by pi divided by 0.0125 squared. And so it looks like about a 328 ohms. So not even 1 ohm, about a third of an ohm, not too much, right? Of course, that's only 1 mile. But here's the real key I want you to see, and one of the important lessons of why our electrical grid system is AC, and why these transformers are so important, and while you'll see them all over the place around the city on our utility poles here, is because how much energy would be lost along 1 mile? Well, we know power is I squared R. Okay, so the amount of power being lost depends not only on the resistance, which isn't that much, but on also the current. And it's the current squared. And that's the big key here. Because if you want to run a whole city or a block of city, aren't you going to need a lot of current going through that wire? Unless you do what? A lot of volts, right. So if we have something that is a power plant here that is generating electricity, and we'll just put it maybe 10 megawatts, so we got this power plant that's going to kind of run our whole city. How much current would have to go through those wires if you generated it at 120 volts? Well, let's see. Power is current times voltage. And so a 10 megawatt power plant at 120 volts would be how much current? Yeah, that's an enormous amount of current. 1, 2, 3, 1, 2, 3. And so this is 83,300 amps. Is how much current you would have to send through that wire. And how much would get lost going 1 mile from the power plant to the city?
What a waste.
Well, I'll go power lost would be I squared R. So I will square that and multiply it by 0.328. And this would be 2.28 times 10 to the, oh wow, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9 watts. I mean, we didn't even generate that much, so obviously that's impossible to lose that much. But here's the lesson. You would lose all the energy you have just created to send it 1 mile to run the city at 120 volts. What's the alternative? Yeah, the alternative here is to not generate it at 120 volts. Or if you do generate it at 120 volts, before you send it on these power lines, step it up to a high voltage. Why is that an advantage? Do you see that? And that's really the lesson I wanted to get here in this first half hour. Wouldn't that give us a lot less current for the same power? And so let's ask this question again. What if the voltage was 500,000 volts? And so those big metal power poles you see hanging, you know, up, well, in our case, you can see them as they string up over the mountains to the other side. And a lot of times when you're driving out, particularly out through the desert, and you're going towards, you know, all the lakes up and down, but I'll pick on Hoover Dam there. And I mean, there's these big power lines. They're all coming 300 miles away, and they're sending all their power here to the coastal California, coming in from the inland California. How much current do you get then if you have 10 megawatts? Which, by the way, I think Hoover Dam is 2 gigawatts, by the way, so we're still 100 times, Hoover Dam is twice, or 100 times bigger than this. But the current now that the voltage is generated at 500,000 is, what is that? That must be 20. 10 million divided by 500, 1, 2, 3,000, and that's 20 amps. And so we only need to send 20 amps through the wire. And so how much gets lost in this 1 mile? Well, 20 squared times 0.328, and we're going to lose about 131 watts. Obviously, any loss is more than we really want, and that's 1 mile, and so if we've got 100 miles or 200 miles, there's going to be a significant amount of loss there, but not nearly compared to the losses that we would have had if we didn't have all these transformers. And so the simple answer is we have these transformers that we start here, we generate the voltage, we step it up to a very high voltage, we transmit it across the country. Then when it gets to the city, we usually step it down a little bit more, so when it's in the city we don't have to deal with 500,000 volts. That's a lot of volts, and those wires are deliberately put really high and really far apart. When they get in the city, you guys will recognize them more in your backyards. You'll look up and you'll see those utility lines. And those will be about 32,000 volts. And so as they are stringing through your backyard, there's 32,000 volts. Again, very important that they're really, really high and far apart. But before they make that final step coming into your house, and I think your author gave you a good picture of the final transformer in the whole sequence, he shows a power pole. Now here's a good power pole. And so that's what you've probably noticed on the utility line. So up here could be 32,000 or 16,000 or an older system 4,000, but it gets fed into here. Here's the looks like the primaries are getting fed into here, and then it looks like the secondary is coming out, and these are the wires that are below that are strung from pole to pole to pole, and these are the ones that come off and feed to your house or your apartment. Those are the ones that are 120 volts. And so the very last step, the very last leg, very little of the distance transmitted is at 120 volts for exactly this reason.
What do they do with all the current? When you step it down, you said if you step down the volts, you step up the current.
Oh, well, let's see, how do I answer? It's distributed by that point because this, okay, so if we stepped it down, this would be the total amount of current, but only a fraction of that goes to one house. Okay, so all of this power coming into the city, each house probably gets about 100 amps. If you go look at your meter in the back, it probably has a master circuit breaker at 100 amps. So
They're all connected. All houses are connected in parallel.
Exactly. So if I divide this by 100 right there, then this could feed 833 homes at its maximum, which seldom does that happen too. So this is probably enough to feed 4,000 homes or something. Yeah.
Wait, so if you fed all the homes at high voltage and then you convert, then you convert then you convert the voltage into current inside the house, you have a dangerously high current and dangerously high current inside the house.
No. Remember, I guess I should emphasize here. I'll go back to the picture here. Here's the primary. Here's the secondary. You still have Ohm's law. So if your voltage here is 120 and you plug something in, let's say you plug something in that has a resistance of 10 ohms, so maybe like a toaster. So the amount of current you get in the secondary is 120 volts divided by 10 ohms, which is only 12 amps.
It'll only feed power.
So it's only feeding it based on Ohm's law. Its maximum may be much more than that, but it's only feeding it based on Ohm's law. So we can't get, all this current. I mean, you could say, well, what if we change the resistance down to 1? Or change the resistance down to 0.1, or change the resistance down to 0.0001. Okay, then you could start getting large amounts of current. Of course, that's why we have circuit breakers in our homes, so that when we get 20, the thing goes click, too much.
I was going to say that the panel distributes the current through different circuit breakers. So.
Right. So, and the transformer is distributed to different houses. So the transformer can only send so much to one particular house. So you're not going to get all of this. So don't think like all that current is. I mean, it's mathematically possible that all that current goes to one house, but it would. Things couldn't handle it. The transformers will shut off. Your panel will shut off. Your individual circuit breakers will shut off. Yeah. Okay. So that's this whole idea, and so it's kind of a fun little history of why Tesla won out over Edison, because Edison said, well, why don't we just build DCs? And he was hooked on DC, and so he just kept building DC, and putting them on these houses. And Tesla said, wouldn't it be much better if we just built one giant power station and then run the wires? And and Tesla didn't get along real well. He said, no, that's crazy. You do that, you got to change the voltage up and down. How can you change the voltage up and down? It's not that simple. And Tesla said, actually it is with Faraday's law of induction. It's actually pretty easy to raise it up. And so obviously you can see what eventually won out. The AC circuitry did. In fact, quick side note, great story. If you got extra time, not now before the final, but to Google the Love Channel, because upstate New York, just outside of Niagara, this guy, William Love, wanted to build a whole new city. Brilliant idea. What he's going to do is he's going to take water out of the Niagara River, divert it through a channel, run it down the channel to one of the Great Lakes, and as the water ran down there, this new city will be on the new technology of electricity. And so the water will run through. We will put a generator at every house, and all these houses will be built, and they'll have electricity, and we'll build factories. And that was his whole plan, because he was thinking DC. And so he bought up all this land and got all these investors and started digging a channel. And then Tesla said, we don't really need to do that. And so he went bankrupt, and some other issues. Eventually ended up selling this dug up channel to the sanitation department, who buried trash, who sold it to a chemical company, who buried toxic chemicals, who sold it to the school district, who built schools. And one of our big environmental movements comes from the 70s, when all this ooze and toxicity was coming out of the ground in upstate New York. And so interesting history of the 70s and the 80s of what actually ended up happening, and the unfortunate health consequences of the people who lived in that area, as this grime and came up from this channel that was once going to be this city of the future, became this big toxic pit that nobody wants to get near. And so, all right. Well, anyways, that was the stuff that I kind of ran out of time. And wanted to take our first half hour and mention it. So let's keep going here. Let's go into the next chapter and do what little we can. But I need to show you this last piece of physics in this last hour that we have, or hour plus. But I want to show you something else before the total time is up. But if I look at the beginning of this chapter 34, there's one last and important piece of physics that was discovered by Maxwell. And probably the place to begin is with this picture. And here is Maxwell's thinking here. He looks at this picture and he says, there seems to be an inconsistency or a problem with our electromagnetics as we have learned so far. And that's this. He said, look, if you were to take a power supply, okay, so there's some voltage V, I'll go back to V, and you put a resistor, say R, and you put some wires, then we know that there would be a current of V over R. And that current would then create a magnetic field. And so, in this case, the current would be heading in this direction. And if I take my right hand and grab it so my thumb is pointing down, I would get a magnetic field that, according to Ampere's law, would be equal to that. In fact, maybe I should put Ampere's law back on here. And so Ampere noticed that magnetic fields were created by this current. And of course, that was our chapter 30. We spent a long time discussing that. But Maxwell was bothered a little bit by that statement because he said, now, wait a minute, what if we add to this circuit? What if that circuit had more than just wires and a resistor? What if it also had a capacitor? And that's where your author starts 34. He starts off with this picture and he says, take a close look at this. According to Ampere's law, you would have current at least until the capacitor became fully charged. Fair enough? In fact, we even had a nice equation. Maybe it's worth putting it on here as we get ready to review for the final exam. But this is what we derived in class for the current in our RC circuit, the time circuit. But this current, as it is flowing through here, would, of course, be making a magnetic field, right? And so Maxwell looked at this and he said, okay, let's do this. Let's have a surface. And he calls this surface number 1. And here's the blue surface. And according to Ampere's law, we have a current. It's going through the surface. Okay, so we're going to have a closed loop. So we take a closed loop and we would get a magnetic field. No problem. But Maxwell was smart enough to realize, what about another surface that is also mapped out by that same contour curve? And in this picture, it's illustrated as surface number 2 in brown. And he said, look, if you were to take a surface and arc that surface in kind of a bow shape, instead of a flat plane, but you make a bow, how much current goes through that bow? None, right? So according to Ampere's law, how much magnetic field should you get? 0. Whoa, now there's a problem, right? One surface says we should get a magnetic field, and another surface with the same contour says we don't get a magnetic field. And that was Maxwell's clue to say, I think there's more to this. There's more to the physics to be discovered than has been discovered to date. And in fact, it was his cleverness, which your author shows as figure number 2, by reversing his viewpoint. He says, all right, let's look at it this way. Let's take the flat surface that is between the capacitor and the bowed surface that cuts the wire. You see, because if we take the bowed surface, doesn't this much work just fine? And so we would get a magnetic field at that place. And then the flat surface, his argument, we must get the same magnetic field. And so his argument is, I can use that symmetry, if you will, to figure out what's missing here. And so he's convinced there's a missing piece, a part of electromagnetics that hasn't yet been discussed. And so this is our grand finale of the semester, our last piece of electromagnetics. He called it a displacement current, I sub d. Personally, I think that's a terrible name, but I'll go with it. And partly is because our terminology has changed. You have to remember that back in those days, the word displacement probably was better described as missing. So he's saying, look, there is a magnetic field, and when you draw surface number 2 through the capacitor, there is some kind of missing current that explains why you should get a magnetic field. You see, when you make the bow shape, you get current. Real current. Real charges that are moving. But when you make the flat shape, you still should get the same magnetic field. But the current's not there. It's missing. And so that's where the name came from. So his first step is to say, look, to understand the physics here, there needs to be more to it. There needs to be what he calls a displacement current. So his second step is to say, well, what would be that displacement current? And here's why I don't like the name displacement current, because it sounds like there is a real current somewhere, and we just haven't found it yet. But the truth is, there is no real current. What is going through surface number 2 that could be the replacement of the real current that is going through surface number 1? Do you see it? An electric field. Exactly. And so Maxwell sees the symmetry here of, wait a minute, didn't Faraday's law give us a second option of creating an electric field? Maybe it's worth repeating here as we come to the end and summarize. Aren't there 2 ways to make an electric field? What were those 2 ways again? Way back at the beginning, chapter 23, how do we make an electric field? Charges. And what's the second way we've been doing recently? Changing magnetic fields. So it is Maxwell who comes along and says, wait a minute, we already know you can create a magnetic field from moving charges. That's Ampere's law. Could it be possible that there is a second way of creating a magnetic field? Could the magnetic field come from a changing electric field? And I hope you are seeing that, yes, as long as current is piling up, meaning the electric field is changing, that's why we get the magnetic field. And so Maxwell added the second and last piece to this puzzle and said, there is another way of creating a magnetic field, and that is from the changing electric field. And so again, I don't like the word displacement current because that makes me think there's some real current around, and there's not. And I want to emphasize, it's not current that makes the magnetic field here. It is a changing electric field that makes it. And fortunately, Maxwell was able to figure it out. He did this. Many of you probably remember Gauss's law. And so Maxwell's logic was simply this, that this real current is what we would use if we were looking at the bowed surface, S1. But if we are using the flat surface, then we would be using this missing current, this new thing he's trying to discover. Now, the real current would be dq dt. If you put Gauss's law with that, then you get that statement for the displacement current. And so I'll solve for Q and put it into here. Maybe to even simplify it a little bit, I'll write this as flux, the subscript E, and an epsilon naught, and a derivative. And so what he adds to Ampere's law is the second piece. Says not only can a magnetic field be created by moving charges, real moving charges, but it can also be created from a changing electric field. And there's the changing part. There's the electric field part. And so this, if you've got a chance to view the textbook, is written in this form, and that completes our electromagnetism. It simply says that there is a second way. Let me say it both in words and in writing and in equations. Now that we are coming to the end, we should say, all right, here is the final piece, and I'll put it together in one big summary, and I'll even put it kind of over here because I want it to stay on the board for the next hour here. But what have we done this semester? Four things. I know it may feel like it was more than four. But what we started off with, I'll call it number one, is we learned about electric fields. And I would say then, electric fields are produced by, and as I've been saying for a while, and hopefully now it's sinking in, is we had two options. The first one is we had just ordinary, everyday, regular charges. We called it Coulomb's law. It was the first thing we got started here. We had charges, that created an electric field. But then, within the last couple of chapters, we learned that a second way of creating an electric field was a changing magnetic field. If I put this in equation form, the integral over a closed surface of the electrical flux is equal to the charge inside over epsilon naught, right? That's our very first statement. Electric fields come from individual charges. Yeah.
Is it you can have a changing area and
okay. I hesitate, but you are right for the next 20 minutes anyways. It's changing magnetic flux. So I'll put magnetic flux. But there's something I want to show you that will prep you for your next level of E&M. Because as much as neat stuff we've done and hard stuff, oh, we've just begun. We're just getting to the good stuff. All right? But this is our basic. This is our fundamental. So yeah, let me change it and write it as changing magnetic flux, which is written as Faraday's law. Faraday's law, which says that I'll write it this way, that the negative change of the magnetic flux is equal to the EMF. That's how we wrote it. But I suppose we could go one step further and say that the EMF is the electric field integrated along some line, some source. So that's what we did back in 27. And I don't think we've done too much of it till today. And this is your 20 minutes that I was getting at coming up here. But this then would be our option 2, if you will. And so now, let's go to magnetic fields. And I would then say, to conclude this semester, that magnetic fields are again produced by ... and we have our 2 options again. The first one is what I would call just a regular current, the moving charges. The conduction current is the word I like, because these are the actual moving charges. These are where the electrons, or if they're positive charges, are actually moving. This is what we would have gotten in that equation if we had done the Bode surface on surface number 1 and say that is the magnetic field. But what I'm trying to add to the last piece is, what's the second way? A changing electric, and I'll put flux field. I'll even come back up here, field, so we can have a further discussion here with the flux and the field here. But this is option number 2. And that is what I'm trying to show you now. This is what started as just Ampere's law has now become Maxwell's law. And so we have an added piece to our puzzle, and that is that we can get our field. So it's kind of interesting how these are separated in 2 different equations, and yet this is in one equation. We can make it a little more symmetric looking if we throw in one more equation. See, this is a line integral. This is a dot one. We did mention it. What was B dot dA over any closed surface? That'd be the flux, the net flux. And what did it have to come out to be? Yeah, good. I heard somebody say 0. Why? Yeah, there's no monopoles. This is the no monopole statement that we got back in when we did our magnetics, the first thing in chapter 30. So maybe I should put a little box around all 4 of these, because a main point I want to get here is that this is the summary of the semester. This is the 4 equations you have done. Now maybe I should throw one more out there. The forces on a charge could come from either electric fields or magnetic fields. But again, if somebody were to ask you, what did you learn this semester? Give them those 5 equations, right? You've got the 4 equations, which are often referred to, maybe unfairly, as Maxwell's equations. He tied them all together, but individual people contributed to them. But this tells us one way of making an electric field. This tells us another way of making an electric field. This gives us both the ways of creating a magnetic field. This tells us there's no monopoles. And this tells us how much forces would be on these charges that, of course, are important because if you put forces on charges, they move. And if they move, they make fields. And if they make fields, they move. And if they move, they make fields. And if they make fields, they move. And this could get quite challenging and very interesting. But this is the grand finale. This is the summary. So in case you were thinking the class seemed like you did a lot of work, let me assure you, I'd say, look, you can fit it on 1/3 of the board. It's just 5 equations, and that's all you did. So I don't mean to belittle it here, but I do want you to see the grand finale. 2 ways of making an electric field, 2 ways of making a magnetic field, no monopoles, and the interaction between our fields and our charges. That's the big story here. I'll leave those there because I want you guys to see some more about those equations in just a second. We'll do that in the last 20 minutes. But let's use this then as an opportunity to say, well, why would I even be interested in all of this? Well, let's look at figure number 5 here for a second. Here's a little diagram that Maxwell noticed right away when he added this piece. Let's talk about it conceptually. Here is where, unfortunately, we are going to run out of time and we won't have the luxury of doing some pretty involved math. Your author will. I'm going to give up all hopes of trying to do the fun math, but try to get the lesson apart nonetheless here. Because, watch this. Maxwell looked at all this, and when he comes onto the scene, a lot like you, they've been working with electric fields and magnetic fields in this sense. Electric fields coming from charges, okay, fine. Magnetic fields coming from currents, okay, fine. But there's another option. And let's ask this question. What if there were no charges someplace, maybe in the atmosphere, maybe in this room, maybe in outer space, who knows? But let's just say there is a field, or could there be a field? And so here's his argument. He puts a grid up here. Here's our grid. X-axis going out this way, Y-axis going up, Z-axis coming out this way. Let's just say there is a magnetic field. If that magnetic field was changing, what would happen? Yeah. So right here, this is saying if I had a magnetic field and it was changing, wouldn't it produce an electric field? And so your author is trying to say, and then he takes some time to go through the math, and like I said, this is where I'm going to run out of time from the math point of view, but he says if you take a loop, and he draws this loop in blue, and if you have a magnetic field, which in his case he says let it point in the Z direction, that would be a magnetic flux through that loop. And according to this equation here, if you have a flux going through that blue loop, it should create then an electric field along that blue loop. And so Maxwell is noticing here, and what I want you to notice here in this last hour we have together here, is that if you have a magnetic field in one particular direction, and it is changing, it must produce an electric field. And its direction should be perpendicular, And again, the math is kind of buried here because this is the flux through the rectangle, so that is one direction, where this is the field along the rectangle that you made. So that's why these two have to be at 90 degrees to each other. But the point is that the electric field is being created from the magnetic field. That's Faraday's law. But here's where it gets even better. And your author kind of turns the picture in the next diagram here. Let's go to figure 6. He says, all right, now that you've seen that one, let's kind of turn this on its side. Actually, no, I guess he didn't turn it on its side. He redrew the rectangle down here. And he says, let's look at another rectangle. Let's look at a rectangle on the XZ plane. Because if you just told me that this magnetic field, which was changing in the Z direction, just made an electric field in the Y direction, then let's talk about this electric field that now has been created. Wouldn't this electric field that now has been created, wouldn't that be electric flux that is going through this rectangle? And our new piece for today is, what are we learning about if you have a changing electrical flux? What will you get? A magnetic field. And so the original magnetic field created an electric field. But what does that electric field do? Creates a magnetic field. And now what do you think that magnetic field is going to do? Create an electric. And what do you think that electric one is going to do? And the next one, and the next one. And what you get from all of this is an interesting interplay of electromagnetics. There are no charges around. Now, don't get me wrong. The original set of charges were needed to make the original magnetic field. But what you are going to get, and he shows this in another figure, I think he's got it as figure 4 here, is you will get a whole series of electromagnetic fields, one feeding another, feeding another, feeding another, feeding another. They'll be at 90 degrees to each other, and one will feed the next and feed the next. Yes?
So basically these fields are just created in thin air.
Even in a vacuum, not even in air, right?
It's created out of
Exactly. So, my little experiment for you guys today is this. Let's see if I can't do something similar. Let me do this. I will take what hopefully is a long untangled wire. I will turn on a AC signal source that's at a pretty high frequency. I will bring it up to, it's about 1.2 megahertz, okay? And I'm going to plug one end of the wire here. I am going to plug the other end of the wire here. I am going to loop this wire around my bench. And what I claim is this little box right now is creating current that goes around this loop and then back and around and back and around and back. And in this case, it does it 1.2 million times every second. Now let's take this one step at a time here. This magnetic field in the Z direction is what I'm telling you I created. Didn't we learn a couple chapters ago that if the current was going around, say, in this direction, wouldn't that make a magnetic field coming out towards you? And then a moment later, the current can go the other direction, so then the current would be the other direction, and so the field would be the other direction. And so the visual picture I want you to have is this loop right now is making a magnetic field that first goes out and then back, and then out and then back. I have a changing magnetic field. That changing magnetic field will then do what?
Is it kind of like a capacitor thing that resonates a specific frequency? And as energy gets moved in one field and it goes to the other field and it keeps doing this until...
Yeah, I'll tell you out of that. Sure. But there are no wires, there's no inductors, there's no capacitors here. And that's what I want to emphasize here. This could be in air, this could be in outer space, but what happens here is, imagine an electric field. That electric field, magnetic field. That magnetic field would create what? An electric field. And what would that electric field do? Create a magnet. What would that do? Electric. And what would that electric do? Create a magnetic. And what would that magnetic do? Electric. So, as I stand right here, is there a field right here? Yeah. And isn't it coming from there? And whatever pattern this current is, which is what makes the field first magnetic, will eventually come over to here and make the field pattern. Let's see if I can even detect it in any way. This radio picks up what we call radio waves. And if you didn't catch it yet, this is what I'm showing you. These are radio waves. I have this thing adjusted to somewhere near 1.2 megahertz. Let me turn it all the way up. If I were to produce the same frequency that this one is tuned to pick up, I should pick it up. I should be picking up something. So I will slightly adjust. Right there is the field it is picking up from me. I am creating what we are going to call electromagnetic waves. The magnetic makes an electric, makes a magnetic, makes an electric, and in this case, A test and another test.